When you look up at the sun, what do you see? Probably a calm, steady disk of light, right? Well, from 150 million kilometers away, that tranquility is a complete illusion. In this explainer, we're going to take a journey from its incredibly violent core all the way to its mysterious outer atmosphere to reveal the true nature of the star that gives us life.
You know, this quote really gets right to the heart of it. That simple-looking star, it's actually a ridiculously complex, magnetized plasma engine. And understanding that engine, well, that's the key to understanding everything from our weather here on Earth to the very nature of stars all across the universe. So here's the crucial thing to grasp. The sun's stability is basically a lie. It's actually a constant, violent battle. You've got gravity, which is always trying to crush it into a tiny ball. And then you have the immense energy exploding from the inside, always trying to blow it apart. What we see as a calm, steady star is really just a long, delicate truce between these two titanic forces. All right, so let's start our journey. We're going to peel back the layers of this deceptively simple object and really dig into the hidden chaos that powers our entire world. And we're starting right at the very center, the furious core. It's only about a quarter of the sun's radius, but this is it. This is where all of its energy is born, in a furnace of unimaginable pressure and temperature. Inside that furnace, one process is king: nuclear fusion. It's called the proton-proton chain, and it's where the immense pressure and heat literally force hydrogen atoms to fuse together into helium. Every single second, this process converts millions of tons of matter into pure energy, creating particles of light called photons and these ghostly little things called neutrinos. Now this is where the story gets really interesting. These two particles, the neutrino and the photon, they're born in the exact same instant, in the same fiery cradle. But their journeys out of the sun, well, they couldn't possibly be more different. First up, you've got the neutrino. This little guy barely interacts with matter at all, so it just zips straight through the entire dense body of the sun and out into space in about 2 seconds. It's basically our near real-time signal from the furnace. But the photon, the actual particle of light, oh man, it's not so lucky. It's constantly being absorbed and then spat back out by plasma particles. Physicists call it a random walk. Its journey, just bouncing from atom to atom, takes on average a staggering 200,000 years to reach the surface. Think about that. The sunlight warming your face today, it began its journey before modern humans even existed. So let's follow that ancient photon on the next leg of its journey. Let's see how this energy fights its way through the sun's turbulent outer layers. This is the sun's churning magnetic workshop. Okay, so this next part of the trip has two very distinct stages. For the first part, our photon is just slowly passed from atom to atom, sifting through this incredibly dense region called the radiative zone. But then, about 70% of the way to the surface, everything changes. The journey enters the violent, boiling convection zone. Convection is a process you've seen a million times. Just picture a pot of boiling water on the stove. Hot plasma, because it's less dense, rises up to the surface. There, it cools off, gets denser, and sinks back down again. It's this constant churning that carries the energy the rest of the way to the surface.
And if you could look at the sun up close, this is what that boiling actually looks like. The visible surface is like a quilt made of these convection cells. The bright centers, called granules, are the tops of those hot, rising columns of plasma, and the dark lanes in between, that's where the cooler plasma is sinking back down into the star. Just incredible.
Okay, so our energy, our photon, has finally reached the surface. But just as we get there, we run smack into one of the biggest unsolved puzzles in all of astrophysics, the million-degree mystery of the sun's atmosphere. This chart lays out the problem perfectly. The surface of the sun, the part we see, is about 5,800 Kelvin. But the wispy outer atmosphere, the corona, which is farther away from the hot core, is blazing at over 1,000,000 Kelvin. It just makes no sense. It's like the air around a campfire being hundreds of times hotter than the fire itself.
So yeah, the question scientists have been wrestling with for decades is simply, why? What in the world is the mechanism that's superheating this thin, tenuous plasma to such insane temperatures? It completely defies our everyday intuition about how heat works.
Right now, there are two main competing ideas. The first is called nanoflaring. The idea is that the corona is heated by a constant storm of tiny, unresolved magnetic explosions, like a field of microscopic firecrackers going off all the time. The second is wave heating, where magnetic waves ripple up from the surface and just dump their energy into the corona. The truth? It's probably some combination of both.
Now, that energy doesn't just stop at the corona. It keeps going. So let's explore how the sun's influence, its energy and its magnetism, crosses 150 million kilometers of empty space to reach us and affect our lives directly, right here on Earth.
This influence usually comes in the form of the solar wind. It's a constant, supersonic stream of charged particles just flowing out from the sun in all directions. This wind fills our entire solar system, creating this vast bubble in interstellar space called the heliosphere.
But the solar wind, that's just the sun's everyday weather. Sometimes, its magnetic field gets twisted up and reconfigures violently, unleashing a true solar storm, a colossal eruption known as a coronal mass ejection, or a CME.
And this is the timeline for when one of these is headed our way. The intense light and radiation from that initial blast, they arrive at the speed of light, so in just over 8 minutes. But the main event, this giant cloud of billions of tons of plasma, it travels slower. It takes anywhere from 1 to 3 days to cross the void and slam into Earth's magnetic field.
And the impact can be really severe. When that plasma cloud hits us, it can trigger what's called a geomagnetic storm. This can create powerful currents that overload power grids, knock out the satellites we rely on for GPS and communication, and even pose a serious radiation hazard to astronauts in orbit. Our modern world runs on technology that is uniquely vulnerable to the sun's violent outbursts.
Which really brings us to our conclusion. After centuries of studying it, after sending probes so close they can practically taste its atmosphere, our nearest star still holds these profound secrets.
You know, we've answered so many questions, but it feels like every answer just reveals new, more complex ones. What is the exact mechanism that superheats the corona? How can we get better at predicting when the next great solar storm is coming? What other fundamental physics is our star hiding just beneath its bright surface?
And maybe that's the most energizing lesson of all. The things we don't know, they aren't failures. As our source material so beautifully puts it, they are invitations. Invitations to look closer, to build better tools, and to just keep exploring. And the sun, our magnificent, turbulent, life-giving star, is very, very generous with its invitations.